Okay, so good morning. So we will start a new topic in today's lectures. We will need either 2 or 3 lectures for this topic. And so, the starting point. So it's called small oscillations, and we'll see what the small mean. Okay, so the starting point is that most systems that occur in nature are stable. You don't see things falling apart and things like that, and so so the idea here is that we will see that this can be quantified in large class of Lagrangian systems. Okay, by Lagrangian system, I mean a system whose dynamics is given by a Lagrangian. Of course, you could do it with the Hamiltonian as well, but I'm just, for simplicity, we'll work with the Lagrangian. Okay, and so also this is the first point. The second point is that many systems large numbers of degrees of freedom, okay, and so we need to be able to handle even
Hello.
such cases. Okay, please mute yourself. Sayantan Paul, please mute yourself. Thank you. Okay, so with this in mind, we will. So we're starting point. Simple. We have some system with Q1, Q2, Qn. These are some generalized coordinates. And there is some Lagrangian, which is a function of the Qi dots and the Qi's. Possibly, okay, so we'll not, let's forget about no explicit time dependence. Okay, we'll make these assumptions. And so we want to ask what exactly do we mean by stability? So let me explain stability first. For 1 degree of freedom, and that's very useful. Okay, and so what we will do is, so if you have 1 degree of freedom, let's draw. Good. So this is QP phase space. Okay, and let's say that there is some point with coordinates say Q0 and P0. No, I don't want that. Okay, so what do I want? Okay, so let's look for a fixed point. So Let's consider say a point Q0. Okay, on the t equal to 0 axis. Okay, so and let Q0 be such that, and let's also make a very simple assumption that uh, L is just T minus V, and V of Q is such that dV by dQ at Q equal to Q0, okay, is 0. Okay, so what does this mean? That if you look at the equation, so let's say this is just some half m q dot square. Okay, so the Euler-Lagrange equations of motion are simple. It says that m q double dot is equal to minus dv by dq. Right? So what does this mean? So when Q equal to Q0, what happens? dV by dQ is 0, so this implies that m q double dot equal to 0, that means no force. Okay, so coming back to this point, so you can see that Q0 and t equal to 0 is a fixed point. Is this clear?
Yes, sir.
Okay. I mean, the force is 0. It started with P equal to 0, so it will remain. So so we can see that, and why is this? So because P dot is also remains 0. Okay, so now the question about stability of this fixed point comes, and we do this by just doing something simple. We keep P 0, but we will now move it to a neighboring point. So this is some neighboring point. Okay, and the question to ask is, so the question is, let Q be close or arbitrarily close to not. Okay, then consider the initial conditions. Initial condition that at time t equal to 0, the system is at Q0 in phase space. Okay, so then the question is not over yet. Okay, will the system remain close to the fixed point at later times? This is the question. Is this clear? So we are asking, if you jiggle it, move it a little bit away, will it? Okay, and the answer is simple. If yes, we say that the fixed point is stable. Okay, is this clear? Is this clear? Okay, so now the question is, how do you analyze this? So the question to you is, how can we how should we proceed to check this?
It is an expand way of doing about.
Okay, so yes, exactly. So study. So we saw that the equation of motion is very simple. It is just this mq double dot. So the question is, what is the force, right? So if you go back to your high school language, is the force restoring or not? That's all we want to ask, right? That's what we would usually ask. Okay. So study the behavior of V of Q near Q naught. Okay, so we do V of Q is some boring constant plus dV by dQ at Q naught times Q minus Q naught plus d square V by dQ square at Q naught into Q minus Q naught whole square divided by 2 factorial plus order Q minus Q naught whole cube. Right, this is the behavior. So first question is, what can we say about dV by dQ at d naught?
Zero.
Zero, right? So this term goes off. So really, this is the leading term. This is a boring constant. So this is the okay. And so this is why I said we can bring it arbitrarily close. Okay, that means we can make what I mean by that. I can make Q minus Q naught as small as possible. Okay, so we can do V approximate of Q. Okay, this is true only. It's just V of Q naught plus d square V by dq square at Q naught times Q minus Q naught whole square by 2. And this will get better and better as we make Q and Q naught smaller if V is a smooth function. Okay, that we will assume. Is this clear? So we have something like this. So now the question, we have, so now there are many possibilities. So there are three, first thing is that, so of course, I said this is the leading behavior, but this assumes that d square V by dq square at Q naught is non-zero. Okay, so let be not equal to 0. Okay, otherwise this is not 0. Okay, so so the question here is, so let's do the following. Let us define. Yeah. So now, question to you is, what should the sign of this constant be? Bad English, so let me just correct it. What is the sign of this term, this constant, that leads to stable behavior? This is the question. So what is the sign? I'm just asking you for a sign, that's all.
Positive.
Okay, it should be positive. Okay, so need. Request, please mute yourselves.
Ama.
Abhishek, mute yourself.
Purila,
Okay, I muted him. Oh, I realized I can mute. Okay. So this is very simple, and then we can define this constant if true. Okay. So let m omega square be defined to be d square v by dq square at q naught. Okay, so then we can see that the and let's define let's do one more thing. Let eta be defined to be q minus q naught. Okay, so the L approx will be half m eta dot square minus half comes because there's a 2 factorial here. Okay, so this is nothing but, so now eta behaves like a simple harmonic, not eta, the Lagrangian. So this is like a simple harmonic oscillator. Okay, for with frequency omega. Okay, is this clear? Okay, so let's do I'll give an exercise. It's a simple pendulum. Okay, if you remember, L would be something like half m L square, some theta dot minus, is it? Okay, plus NGL cos theta. Is this correct? Whatever it is, up to some constants. Cos theta is 1 minus theta square. Okay, perfect. Okay, so here the fixed point is, what is the fixed point? Okay, so do the small show, I mean, so what is exercise? Show that omega equal to root L by G or G by L. Correct? By repeating. This we can easily check. Okay, so just do this exercise, which will illustrate this simple idea. Okay, so, but let's ask what happens. So that's one thing. So generic solution, the eta of q, okay, is equal to some a e power I omega t plus b e power minus I omega t. Actually, let's write a different form. Right, this is what it is. Okay, and so if you are told that eta at 0 is 0 and eta dot at 0, sorry, eta at 0 is not 0 but eta some constant. Okay. We can fix a and b can be fixed. Okay, so that I leave it to you as a, so yeah, I mean, in fact, so can someone tell me the answer to this? There's a reason I wrote it in this way. Okay, so coming back to this picture that we had here. So you start out something, so it's going to go, and there'll be some ellipse kind of thing. It will do this. Correct? So it'll remain in that neighborhood. It's not going to go away some arbitrarily far away. There will be some bounds you could put depending on the value of q minus q naught. Is this clear? So this is stable. Okay. What about the other situation? Now what happens if, okay, if that q naught is less than 0? Okay, so then the L approximation will look like this, half m eta dot square. Now I'll just define, then we can have m omega square eta square. There's a plus sign here which is crucial, and I'll just define this to be the negative, so I'll call this minus m omega square. Okay, that's how I define omega. Now because of this all important sign, okay, what we will get is eta of t is equal to a cos omega t plus b sine hyperbolic omega t. Okay, again I could have written it exponential. Okay, so now again same boundary condition. So eta at 0 is eta naught, and eta dot at 0 is 0. So what is the solution to this? Are there people? I mean, this is how I do this. I just look at it and say, okay, I want eta dot at 0 to be 0. So I cos hyperbolic derivative will give me a sine hyperbolic, which vanishes, so that a is not 0. But cos hyperbolic, b sine will get, when you differentiate once, will give you cosine hyperbolic. So that b should be 0. And then a I'll fix this way. So again, you get eta of t. What was sine, cosine becomes now. Okay. And what is the behavior of cosine hyperbolic for large t, large positive d? T?
E power omega t upon.
Okay, so this goes like eta e power plus omega t for large t. Okay, so you can see that it goes away, so it diverges. So the system moves away from the fixed point. Okay, so this is unstable. That's why it's unstable. Okay, so that's a third possibility. So okay, and what happens if d square v by dq square at q naught is 0? Okay, then we need to go to cubic order. Okay, and if this is non-zero, what will happen? If the cubic, that means if this means cubic term. Okay, so we'll get v of q, give me some v of q naught. So first two terms are 0, it will be plus 1 by 3 factorial d square d cube v by dq square cubed at q naught into q minus q naught whole cubed by 3 factorial plus higher order. Okay, question to you now. is there a sign which we can assign to the third derivative to this constant which will make it? So what sign? Anybody has answers to this?
Yes, and yes, and it will be stable in one direction, then it will be unstable.
So no sign will help. So if it's a positive, then on the positive, if q minus q naught is greater than 0, it will be stable, but then on the other side, it will be unstable. So this is still unstable. Answer is no sign. Right? That's what you were saying, Jay. Right?
Yes.
Yeah. So no sign works. Okay? It is unstable. But now suppose cubic term is 0 and quartic is non-zero, again you get stability. So you will see that as long as there are if the leading power is odd, then it will be unstable. If the leading power is even, it will be stable. You can convince yourself. Okay, so okay, and if all derivatives vanish, that means it's a neutral equilibrium. Okay, so that is a very, very special case. In 1D, it is very artificial. Okay, but in higher dimensions, we can get. Okay, so this is the kind of thing. Okay, so let me just draw one graph and then for 1D. Okay, suppose I have some potential like this. Okay, so now here we can see that I'm marking with X's all regions which all fixed points, right? So we have 5 fixed points here. Okay, so let's call them Q1, Q2, Q3, Q4, and Q5. Okay, so now question to you is, which ones are unstable?
Q2, Q4.
Okay, so let's do that. So let's
Q2.
Q2 correct, also Q4 because it's negative this thing. Okay, the stable ones. Okay, so yellow is stable, red is unstable. Yes, this is our color coding. Okay, and so you can see that these things. So let me explain why. I mean, these are all stable, but you can see that if you ask for a global minimum, Q1 is global minimum, right? But we are only interested in small oscillations, so we'll stick to some small neighborhood, say like this. Okay, where you will not see all the other points. That's the idea. So that's what we mean by small oscillations. We don't consider oscillations that are really, really tiny. Okay, is that clear? Okay, so these are all stable viewpoints, these things, and so for small perturbations, this is the conclusion. So very, very nice. So we just reduced it to looking at the extrema of the potential. Okay, so we need to generalize this idea to higher dimensions. Okay, so we should also, okay, that we want to do, and we also want to write more general kinetic energies and Lagrange. Okay, so let's sort of try to write something. L should be a function of the qi dots and q's. Okay, I will call this half. Okay, so by this I mean, so for instance, if you, I'm going to allow Tij to depend, depend on coordinates. Okay, by Q here, I mean all coordinates times Qi dot Qj dot. So this is the kinetic energy minus some arbitrary potential. Okay, so this is the form. So we are looking, so kinetic energy is taken to be quadratic. Okay, in velocities. Okay, this is going to be the kind of Lagrangian system that we will consider. Okay, and this is fairly generic, and also takes into account that the coordinates need not, I mean, so for instance, in the example I just did, which was Cartesian coordinates, but in the exercise I gave you, it was not Cartesian. But so you can, so we have to, but the coefficients at least were constant, and it's useful to think of Tij of Q as a symmetric. Why symmetric? I'll let you think about n by n matrix. There are n degrees of freedom. Okay, what do I mean by that? It's like this. Right, so T okay. I didn't write it as a symmetric matrix, so let me do that. Oh, okay, so I've done that. Okay. So question 2 is why, first thing is why do I lose anything by taking Tij to be non-symmetric? Suppose, what happens if I said Tij is antisymmetric? Just be extreme. What happens to this first piece, the kinetic energy piece?
Cross terms would vanish. Qi.
It'll be zero. It'll be zero.
Right.
Because Qi, Qj under these are symmetric, and okay, so if this is antisymmetric, okay, it will vanish. So, but if you write a general arbitrary matrix which is neither symmetric or antisymmetric, we can always write an arbitrary matrix as the sum of a symmetric matrix and an antisymmetric matrix. But the antisymmetric matrix will give you 0, so you can just replace the generic matrix by its symmetric part. That's what it means. So there is no loss in generality by saying that I am saying that Tij is symmetric. Is this point clear? Okay. So, and of course I didn't say this is functions of, this is a function of Q's, of course. Okay, so, okay, once we do this,
But sir,
yeah.
uh, if we write general matrix as a sum of symmetric and antisymmetric, and in antisymmetric the cross terms will vanish, but still there are diagonal terms which remain.
In an antisymmetric matrix, I think
Oh,
the
0.
diagonal is 0.
Okay. Sorry, sir.
It's okay. It's okay. No, it's good to have these kind of questions. Okay, so then the kinetic energy can be written nicely as a matrix. So form this called a row vector T column vector. Okay, so let's write the Euler-Lagrange equations of motion. It says d by dt of dl by dqi dot should be equal to dl by dqi, right? Right, isn't this what it says? Okay, so first let's write the left hand side. One second. Okay, repeated indices are summed over now. Okay, is this correct? I mean, I wrote LHS, but actually I've written the full equation of motion, so I remove this. Is this correct? Okay. Is it okay or not? Waiting for
Yes, sir.
somebody.
Yes, sir. Yes,
It's
sir.
okay, right?
Yeah.
I didn't make any mistakes. But now the point here is that, yeah, there are all these other terms which are there, but they are there. I mean, the equation of motions is the equation of motions. There's nothing about it. But the idea of a fixed point would be that, you put all the qj dots to be 0 for all j equal to 1 to n. But further, we just say that dv by dqj for all the q I is equal to some q naught I is 0. We need the forces in all directions. Okay, so that means forces in all. There cannot be any exception. Okay, all directions vanish. Is this point clear? Okay. So we are, so the thing is, all these q dot terms and all vanish at that fixed point, and so then you will just get qi, you will get tij. So so at that neighborhood point, it will look exactly. So this is the definition of a fixed point. So fixed points. In the end. Somebody should give a concert at least. Fixed points are determined by extrema. Is this clear? So this is the. So it's not too different. Not too different. From the 1 degree of freedom case. Okay, so, but now we want to study stability. This is where we do the same thing. Expand about, say, let's write a vector about q dot. So we get v of q now partial derivatives plus higher order terms. Okay. So now the question is, we have to use the fact that q naught is this thing. So what does that tell you? Some term vanishes, right? Which term vanishes? Anybody alive?
Second, first derivative.
Okay. First derivative vanishes. So we get again. So let's we want to write an approximate potential. So let us study the matrix, the Hessian, right? That's what matrix of second derivatives. At q equal to q naught, it's called the Hessian. It's called the Hessian. Okay. So what does that mean? So it says, I did something wrong. Okay, so this is a matrix now, right? You can see it's an n by n matrix. Okay, so it's a symmetric. What am I doing wrong? Okay. Okay, so let's again define this n by n matrix V, which is defined to be all at q naught, evaluated at q naught. So this is an n by n matrix. Is this clear? This is called the Hessian matrix. And so what we will get is, so we obtain, so then the approximate V approx will be some constant, Boring constant at Q naught plus, and let's call eta I, let's define it to be Qi minus Q naught I. Okay. Okay, is this clear? This is what we get. Okay, so this is V approx, and so we can ask what happens to T. We can here also we do an approximation. Okay, and the approximation is the following. So half Tij at Q naught times eta I dot eta j dot plus dot dot dot. Okay, so the point here is that I could have what I have done here is that we are keeping only. So I could have so you can ask, for instance, I could have expanded this as a power series, and so I'll write something like this: dk Tij at Q dot, okay, times Q minus Q naught. So I can just write eta k. I could have written this, but what we think of eta as small, and in the Lagrangian we keep terms only which are up to quadratic powers. Okay, so this will give, so you will see there's one eta k here. This term will be cubic. Okay, so this leads to cubic terms. Okay, so coming back to this Euler-Lagrange equation, if you remember that we had, so we were looking at terms, these kind of terms like this. There's one more when this d by dt hits this. These kind of terms will be lower order in our, will be neglected. Okay, so now I'll stop by writing an L approx, which we will solve next time. Okay, L approx, which would be half matrix T minus half times yeah, now I remember. Oh, it's T minus V, so I'm fine. So minus okay, so this generalizes in the one degree of freedom. We just got everything quadratic and nothing else. Okay, there's nothing more. So this is the version. So this is the one. So L approx determines the stability. Okay, is this clear what we have done? I am doing some truncation, and that's it. Okay, so this, so I throw out terms like this. So what I've done is throw out terms like this. I'm not saying it's not there in the exact thing, but we want to just study the behavior, and so something which is order eta cubed, eta power 4, we are throwing out left and right. So even eta dot. So we are saying eta dot, we don't distinguish between them. They're all small. Okay, and of same order. So there are these tricks which you can say that eta scales like lambda eta, and you keep only terms which are, of order lambda square in the Lagrangian. Okay, so this we will see how to solve this, and okay. So now, but the point here is that you will see that this is much more intricate, because there are these T and V are all we know about them are symmetric matrices, which is nice, but so we will see that we can reduce this to solving a particular kind of eigenvalue problem, and we will see that the eigenvalues can be associated with, so the signs of the eigenvalues will determine the stability. So just as we saw that d square v by dq square should be. Okay, so even here, if T were identity, this T were identity, then more or less it will decouple. We could think of diagonalizing V. Okay, maybe we'll do that next class. Okay, so but is this clear? What we have done, we have simplified the story because we are only interested in the dynamics arbitrarily close. So eta can be made as small as we want. Okay, so that is the idea of small oscillations. And so this problem, this is what we will solve next lecture. Okay, I'll pause for some questions or comments. Okay, so remember that this T and V were defined. V was the Hessian at the fixed point, okay, and T was just the kinetic energy matrix at the fixed point. Okay, so I should call it T of Q now. Okay, sorry, I defined something called T of Q, where T, yeah, this is, yeah, let me just write that. T is to be what I call T of Q naught. Okay, so this is the kinetic energy matrix at the fixed point. Okay. Any questions?